Can
So
you see my slides here?
now we can see it. So thank you, and you can just go ahead.
Excellent. So thank you very much for the invitation, and I'm excited to talk at the seminar today. And please, if you have any questions, either put them in chat and Rasmus will notify me, or turn on your audio. I'm not exactly sure how AirMeet works, but notify me in some way, and I'll answer them.
Oh, I can actually say this. So we are able to put people up on stage if they want to turn on their mic for asking a longer question. So if anybody in the audience wants to do that, they can just say in the chat, and we
Great,
can.
excellent. So yep. So today I'm going to be talking about pseudorandomness for unbounded-width branching programs. And this is based on joint work with Salil Vadan, Andrzej Bogdanov, William Hoza, and Gautam Prakriya. So I'll give an outline of the talk. First, we'll give some motivation for for the general derandomization problems that we're going to be thinking about. Second, I'll introduce the most conventional approach to derandomization in some sense, which is the idea of a pseudorandom generator and pseudorandom generators for one of the models we're going to be talking about. And then for the rest of the talk, I'll talk about two relaxations of this second line. First, a new type of pseudorandom object called weighted PRGs, or a recent type of pseudorandom object called weighted PRGs. And second, some relaxations of the model called permutation and regular branching programs. So the most important question, or the motivating question of the research in this talk is, does randomness help save space in computation? So this, in terms of complexity classes, is BPL versus L. And the conjecture is that for every randomized algorithm that uses order log n space on inputs of size n, there's some deterministic algorithm that decides the same language and uses only a constant factor more space. So we believe this to be true, and unlike in the time-bounded case of BPP equals P, there's been some exciting unconditional progress on this. And so the most natural way to look at this problem is likely via pseudorandom generators. So here we say that a function g, which takes s bits of seed to n bits of output, is an epsilon PRG for some class of functions on n bits to 1 bit, if for every function in that class, the expectation of the function under the uniform distribution on n bits, which I'll denote un for the talk, is within an additive error epsilon of the expectation of the function under uniformly random output of the PRG. So we say that the PRGG is explicit if we can evaluate it in space order S given input X. And this is important because if we'd like to turn a randomized algorithm into a deterministic algorithm using a PRG, we'd like a PRG that we can evaluate without increasing the space complexity of the algorithm. So we can then compose the two things. And so our goal for this talk, therefore, is constructing explicit PRGs with order log n seed length that fool log space computation. In order to do that, it's worth formally modeling how log space algorithms use their random bits. And the way we're going to do that is via ordered branching programs. So if we have some small space algorithm, A, which takes in an input X and a random string R, we can fix an input X. So just consider any input that we'd like of length n, and now consider the action of the algorithm over its random bits. And we can model this using this ordered branching program. So we start at some start state, and from this start state, we read the first random bit, R1, and if the random bit is 0, which I'll just denote with blue edges for this talk, we transition according to the 0 edge, and if the random bit is 1, we transition according to the 1 edge. And we do this for time step 1, we arrive at time step 2, then we transition according to the value of the next random bit, et cetera, et cetera. And so we think of there as being n layers for n random bits, and we can use this to model memory-bounded computation by saying that we label the states in layer I with the memory configuration after reading the ith random bit. So maybe we start here at the all zeros memory configuration at the start, and then these are the transitions that correspond to reading the values for the first random bit. And by doing this, we can model a program that uses n random bits and s bits of working space as an ordered branching program with length n and width 2 to the order s. And so what this means is if we consider ordered branching programs parameterized by their width, so we say that the length is n and the width is w, if we have some algorithm which uses order log n space, it'll have width 2 to the order log n, which is poly n. So in some sense, the case that's most relevant for space-bounded derandomization is where you have a program of length n and width poly n. And so here's just an example of that program being evaluated on an input. We can see that the first bit is 0, the second bit is 1, third bit is 1, and we reach this state, which is marked as an accepting state. And if we reach an accepting state, we say the program evaluates to 1. And if we don't, we say the program evaluates to 0. And so it's not too hard to show via the probabilistic method that there's a PRG for ordered branching programs with seed length order log nw over epsilon, and moreover, this is optimal. So you can't do better. So in 1990, Nissan constructed an explicit PRG. So the probabilistic method does not give you an explicit PRG. So Nissan constructed an explicit one with seed length log n times log nw over epsilon. So in terms of our dependence on all of the parameters, the length n, the width w, and the error epsilon, this is a factor of log n away from optimal. Unfortunately, this is still the best known PRG for ordered branching programs of width anywhere from 4 to polynomial in n. And so that motivates us to think about other models or other ways of approaching the problem. In particular, we can think about other pseudorandom objects rather than PRGs, and we can think about other models rather than ordered branching programs. So for our first relaxation, we'll first view, we can think of a PRG as saying that the average on a small set of strings is close to the true average for every function in this class. And so rather than requiring that the average on the small set of strings output by the PRG is close to the true average, we can require the weighted average of the function on these set of strings to be close to the true average. So here, this is a lot of notation, but I'll try and highlight the differences. We say that this tuple of functions, g comma rho, is an epsilon weighted PRG for a class of functions if for every function in this class, we see that we pick a random string, evaluate the function on the output of g, and then multiply by this weight function rho, evaluated on this seed. And if this weighted expectation is within epsilon of the true expectation of the function, again, where we're comparing to the true expectation under uniformly random bits, we say that it's an epsilon weighted PRG. And this tuple g rho, we can see that g takes an s-bit seed to n bits of output, and rho takes an s-bit seed to some real number. So we've added the ability to multiply by these coefficients that we choose, and so a normal PRG is just a weighted PRG with the rho function always equal to 1. And so this definition is more flexible, but we can use a weighted PRG for derandomization where we're previously using a PRG. And this is because if our goal is to estimate the expectation of some function to within epsilon, we still get that estimate by enumerating over all the seeds and computing the weighted average. And furthermore, it can be shown that if g rho is a weighted PRG, then g is a hitting set generator, which I have not defined yet, but I will later in the talk. So now that we have this new definition, the very exciting work of Braverman, Cohen, and Garg that introduced the idea of a weighted PRG constructed an explicit weighted PRG for ordered branching programs with seed length O tilde, so I'm hiding some log factors, log n times log nw plus log 1 over epsilon. So what we've done here is we've gone from the dependence on the error parameter epsilon being something like log n times log 1 over epsilon to now we have this O tilde plus log 1 over epsilon. So this is a near optimal dependence on the error of the weighted PRG. And then there was a series of subsequent work by Chattopadhyay and Liao, Cohen, Duran, Renard, Sperlo, Tashma, myself and Vadan, and Hosa, which led to an ultimate result by Hosa constructing an explicit weighted PRG for ordered branching programs with seed length log n times log nw plus log 1 over epsilon, with no more log-log factors. So what this result does is it matches the dependence of the Nissan PRG on the length n and the width w, while at the same time achieving optimal dependence on the error parameter epsilon, up to constant factors. So this is really nice, and what unifies the final three works in this series are that they're error reduction results. So Braverman, Cohen, and Garg was a involved explicit construction of a weighted PRG, and then the three final works really are a simple way to reduce error in a way that I'll talk about next. So to state this more formally, the result that I'm going to talk about, which was obtained independently and simultaneously by myself and Vadan and Cohen, Duran, Renard, Sperlo, and Tashma, states that given some error parameter, given some desired error epsilon, and an explicit 1 over n squared PRG for length n width w ordered branching programs, we can turn that 1 over n squared PRG into an explicit epsilon weighted PRG. So epsilon is our desired error parameter, which would be much smaller than 1 over n squared, for instance, for length n width w ordered branching programs with seed length s. So this was the seed that we started with. And then we lost something like log nw over epsilon, additional bits of seed. And this is very affordable because if we're going to construct an epsilon weighted PRG, it needs to have seed length at least log nw over epsilon. So minus the log-log factors here, which I'm not showing, this is essentially an optimal dependence on the error. And just to outline the third result, which I will not be discussing in this talk, but it proceeds along similar ideas with some additional insights, the work of Hosa establishes that if you're given a PRG with error 1 over n times w, so length times the width, then there exists an explicit epsilon weighted PRG, where now the dependence is an additive order log nw over epsilon, which is optimal. So at a high level, all of these results interpret space-efficient algorithms for estimating random walk probabilities of Ahmadinejad, Kellner, Murtaugh, Peebles, Sidford, and Vadan as weighted PRGs with large seed length, and then derandomize. And so now we're going to move to viewing branching programs as directed graphs. So one natural way to think of a branching program is as a directed graph on n plus 1 layers, where all of the edges go from layer I to layer I plus 1. And with this definition, we can define, in a very conventional way, the Laplacian of a branching program. And this is analogous to the definition of the Laplacian for a directed graph. And we have on each diagonal, we have the random walk matrix of layer I of the branching program. So what does this mean? It means the random walk matrix, the W times W matrix, that contains the probabilities of going from a state in layer I to a state in layer I plus 1. So this is sort of a single step in the branching program on one of these layers. And so we define the Laplacian in this way, and now we can start thinking about using tools from spectral graph theory to help us obtain pseudorandom constructions. So it's not too hard to show that the inverse of the Laplacian of the branching program has this following form, where for each block, we just have the product of the random walk matrices from layer I to layer J. And in particular, this final block, the 0nth block of the matrix, contains random walk probabilities from the initial layer of the program to the final layer of the program. And that's exactly what we want to estimate when we're constructing pseudorandom objects. And what this means is that an accurate estimate of L inverse implies an accurate estimate of transition probabilities in the branching program. Because of this, given the Laplacian of a branching program and an approximate inverse, L inverse tilde, we want to measure how close L inverse tilde comes to inverting L. And so rather than comparing these two directly, like subtracting them and look at the norm of that, we instead compute L inverse tilde times L and subtract off the identity. And we call this the error of our approximation. So if L inverse tilde is exactly the inverse of this matrix L, this is 0, which is good. So we have 0 error if we're perfectly correct. And otherwise, we can measure how close we came by measuring the norm of this error matrix. So the important but very direct result that we use is the idea of preconditioned Richardson iteration. So suppose this error matrix that we've defined in terms of our weak approximation has norm delta less than 1 for some submultiplicative matrix norm. And this matrix norm is actually going to vary depending on which result we're going to use. So just some submultiplicative matrix norm. Then for every k, we can construct the LK inverse tilde, so the kth order approximation, which just consists of powers from 0 to k of this error matrix times our weak approximation. And then if we measure the quality of this approximation with regards to the same notion that we've been using, we get that our boosted approximation is a delta to the k plus 1 approximate inverse. And we have this delta to the k plus 1, and so our error is decreasing exponentially in the number of iterations k. So this is great, and in fact, preconditioned Richardson iteration, why it works, has a very simple proof that I can just give on one slide without even adding any words. If this doesn't make sense, don't worry about it, because it's not a big deal, but we just roll in the definition of the kth order approximation. Then we note that L inverse tilde times L is exactly the identity minus this error matrix that we defined earlier. And then we observe that this is a telescoping series. And so the error of this is exactly the error matrix to the k plus 1 first power. And then the reason we go from here to our high quality approximation is you can add your favorite submultiplicative matrix norm to all of these terms, and then use that this is at most delta to the k plus 1. And so we want to go from preconditioned Richardson iteration, which is a tool for improving approximations for graph algorithms, for instance, to constructing a pseudorandom object. So it's not immediately clear what these two things might have to do with each other. Because, for instance, for preconditioned Richardson iteration, we were looking at our L inverse tilde. We were looking at our approximation. But when we're constructing a pseudorandom object, we don't have the ability to do that. And so the key idea behind these results is to interpret Richardson iteration as oblivious error reduction. So reducing the error of a construction without knowing exactly what's going on inside the error reduction procedure. What we're going to start with is we're going to start using the Nissan PRG, so this great explicit PRG defined earlier, which takes a seed of S base bits and produces n bits of output. And we want to approximate these transition probabilities from layer I to layer j for all possible I and j. So there are n squared of these, and we're going to approximate each of them to error 1 over n squared. And what we're going to do is we're going to stick these approximate inverses in our weak estimate. So the true inverse has the exact product here, and instead we're going to put our estimate of this product that we obtained using the Nissan PRG. And just a note that from the seed length of the Nissan PRG, this base seed length is log n times log nw. And so with the Laplacian and our weak estimate as defined before, we can just compute what this error matrix looks like from the definition, and we get that it's a block matrix with this form. So looking at the entries of this block matrix, for entry I comma j, we have two terms. We have our approximation of the walk probabilities from I to j minus 1 times a single truly random step. So the transition matrix from I to I plus 1 is the equivalent of taking a truly random step on that layer. And then we subtract off our approximation from I to j. So we have the difference of these two methods of approximating probabilities from layer I to layer j, and we have that for all possible pairs of layers. And so the ijth entry of this error matrix is basically the PRG output on layers I to j minus 1 concatenated with a truly random bit minus the PRG output on layers I to j. And so by taking a union bound over the n blocks per column, it's pretty direct to show that the L1 operator norm of this error matrix is bounded by 1 over n. So here we just look at this column has the most number of approximations. Each of these approximations is a 1 over n squared approximation, and there are n of them. So this is a very direct bound, not using any powerful machinery here. And then we can further examine, now that we have the structure of the error matrix, we can examine the structure of Richardson iteration itself. And so if we consider the 0nth block of the kth order approximation, we have that it has this maybe strange looking, but very direct, very sort of explicit form, where for every set of indices, I naught up to IR for R and most K, we have a product of these approximations where for the first product, we go from I naught to I1, and then for the second product, we go from I1 to I2, et cetera, up to this final product, and then we add a final approximation, which takes us the remaining number of layers to layer n. And because we know that preconditioned Richardson iteration produces a high-quality inverse, or produces a high-quality approximation, we know that this block minus the true random walks from the initial layer to the final layer is an n to the minus k approximation. And so this is a sum over partitions of 0 to n, where each segment consists of an independent draw from our base Nissan PRG. And here we use that this is effectively a linear combination of PRGs, and a linear combination of PRGs is a weighted PRG. Because now that we have the freedom to choose these row coefficients, we can do things like add PRGs, and we can do things like take the difference of PRGs. And this freedom to incorporate these row corrections allows us to write this whole expression as the branching program composed with a weighted PRG. And we can see that we have some minus signs appearing here, and because of this, we're actually going to get negative coefficients in our ultimate weighted PRG construction. And so this was not possible to do merely with a PRG as our desired pseudorandom object. So now, sort of recalling that we chose our error parameter delta to be 1 over n, we choose the number of iterations so that the induced weighted PRG by this construction is an epsilon weighted PRG. So now we can think about what is the seed length of this induced weighted PRG. In order to generate an output of it, we need to do two things. We need to select a partition of the layers n into k different components, and then we need to generate seeds for those independent draws from the base generator. And so the first part of the construction has seed log n to the k, and by the way we chose k, this is order log 1 over epsilon, so this is optimal, no issue. Unfortunately, generating k independent seeds, each with those seeds having seed length s base, gives us a seed length of k times log nw, which is actually worse than the Nissan generator that we started with. So we seem to have made no progress here. But the further observation that we can use is that this k is very small. And so we can then derandomize these independent draws using existing tools. So if we think about one of the terms in this Richardson iteration, we can see that it's this base generator G composed on some seed, S0, followed by G composed on S1, S2, etc., etc. And these are over these various subsets of layers, which are specified by the indices. And so rather than using independent seeds, S0 through Sk, we can correlate the seeds using the Impagliazzo-Nissan-Wigderson pseudorandom generator. And because we're going to do this to every single term in our eventual weighted PRG, and we're going to take a union bound, we could take the error of this inner PRG, this INW PRG, to be epsilon over the number of products that we want to derandomize. And so there's something like n to the k products that we want to derandomize, and so we get our inner error to be epsilon over n to the k. And so the new inner seed length is the INW PRG has the same seed length as Nissan, but rather than needing to create something of n layers that we want to derandomize, we're instead just derandomizing k successive PRGs. And so we have this originally log n term, but this log n term is now log k. And because k is already only log 1 over epsilon, this is going to turn into some log term, which is almost going to vanish. And so now that the length of this construction is very small, if we then going to pay log w times n to the k over epsilon, this is going to turn out to be something like log base n of 1 over epsilon times log n, which we can afford, because this is going to be nearly optimal up to log factors. And so we can afford to use this conventional derandomization technique because the number of iterations we did is very small. And so by doing this, we construct our error reduction result, and we're able to go from an explicit PRG with seed length log n times log nw over epsilon to an error reduction result saying, taking a base PRG, we can get nearly optimal dependence on this error parameter epsilon, as at the cost of going from a PRG to a weighted PRG. So this is exciting, or I think it's exciting, but there are two limitations of this approach that maybe you've spotted. The first is that because we did this very crude bound on the L1 operator norm of this error matrix, we needed to choose the base error delta to be something like 1 over n squared in order to get the norm of this error matrix to be less than 1, and so in order to get convergent iterations. And even worse, even if we managed to construct some improved analysis of Richardson iteration, such that we could take the base error to be something like a constant, like 1/3, and even if we just specialize to thinking about branching programs of width 4, so the smallest case where we don't have improved progress on PRGs, because we're using the Nissan generator as our base PRG, and because the Nissan generator has this log n times log n term, our S-base seed length is still going to be omega of log squared n. So right now, these error reduction results require small error, and even if they didn't require small error, the base PRG seed length would still present this barrier. So one natural question is, how can we evade these limitations? One way we can evade limitations on ordered branching programs is by considering a more restricted model. So we're first going to look at regular branching programs. So regular branching programs are a subset of ordered branching programs where the transition graph at each layer is 2 in regular. So here's an example of one, and we can see that there are 2 edges leaving every state because there's an edge labeled 0 and an edge labeled 1, but here there are exactly 2 edges entering every state as well. So it's not the case that we could send all of the transitions from layer 0 to this state in layer 1. They need to be spread out. And in fact, we can consider a further restriction. We can consider permutation branching programs, which are regular branching programs where the 0 transitions at each layer and the 1 transitions at each layer define permutations on the states. So here we see that this is the edges are the same, except that I've changed the colors on them, which means I've changed which ones correspond to zeros and which ones correspond to ones. And we can see that reading a 0 in the 0th layer, you get a permutation going onto the first layer, and same if you instead read a 1, and this is the same for all of the layers. So there's been extensive prior work on pseudorandom objects for regular and permutation branching programs. So Nissan has an explicit PRG with seed length log squared n plus this other stuff, and Braverman, Rao, Raz, and Yehudioff were able to eliminate this log squared n term for regular branching programs. So they get a seed, log n times log w over epsilon, hiding some log-log factors, and then a simultaneous series of work obtained explicit PRGs for constant width permutation branching programs with seed length log n times log 1 over epsilon. So here there's no more log-log factors, and I'm hiding the dependence on w, but if we consider w to be a constant, that's okay. But unfortunately, these works are really exciting, and they eliminate an important part of the seed length, but they don't beat Nissan in the polynomial width regime motivated by derandomizing log space computation. And this is because if you plug in w equals poly n here, you'll get this log squared n term, which will reappear. And the same thing will happen here, except it'll be a little bit worse because the dependence on w is worse than that. What's happened here is that these prior results have came up with improvements on Nissan for small width regular and permutation programs. Now, these results have a dependence on width as well, but one thing we might want to think about is, in general, what does the small width case say about the large width case in terms of pseudorandomness? So, for instance, suppose we have a fantastic PRG for permutation branching programs of width 2. Is this PRG good against permutation branching programs of width 3? So how does a construction degrade as we increase this width parameter? Because we'd eventually like to make this width parameter polynomial in n. Here, we can consider this PRG, which just consists of all strings with Hamming weight 0 mod 3 in 0, 1 to the n. You can show that for permutation branching programs of width 2, G is a fantastic PRG. In fact, you have exponentially small error. So this is pretty much the best you can do. Unfortunately, against permutation branching programs of width 3, G is not even a 1/4 PRG. So we've increased the width by 1 and gone from exponentially small error to constant error. And the reason for this, or the construction for width 3 that makes this fail, is that branching programs of width 3 can compute the sum mod 3. So the program that computes the sum mod 3 and checks if it's 0 will accept every string in this PRG and will accept approximately 1/3 of truly random strings. And so this will be very easy to distinguish from uniform. And so in some sense, what this means is that restrictions on width are brittle. But on the other hand, directly improving the large width case is very hard. So the next thing we might want to ask is, what else can we restrict? So rather than restricting the number of states in every layer, which is effectively what setting the width parameter does, we can instead choose to only restrict the number of accepting states in the final layer. So in an intermediate layer, you're allowed to have as many states as you like. But in the final layer, you're only allowed to have a certain number of states that are marked as accept. This is a generalization of the bounded width case, because a program of width w can definitely be written as a program with w accept states. Because if you only have w states in every layer, then giving you the ability to add new states in intermediate layers doesn't really matter, and you definitely have in most w accept states in the final layer. So we have this inclusion that's showing we're generalizing the bounded width model. But what's really nice about bounding the number of accept states is if we have an epsilon PRG, or a weighted PRG, or a hitting set, which I still haven't defined, for programs with one accept state, that construction is an A times epsilon, whatever object it is, for programs with A accept states. So we have very mild degradation as we increase the number of accept states. Our error will go up, but it'll go up by a multiplicative factor of the number of accept states. Whereas previously, we could go from exponentially small error to constant error by only adding a single additional, by only increasing the width by 1. So maybe this is motivation for why this model would be interesting, but we still haven't actually talked about what the model can compute. So how powerful are unbounded width branching programs with a limited number of accept states? And we'll start with the weakest possible case. We'll only allow a single accept state. Unfortunately, ordered branching programs with unbounded width with a single accept state can compute all Boolean functions. So this is not an interesting model. It's impossible to create pseudorandom objects for this. It's not doing anything. Luckily, if we instead consider regular or permutation branching programs with a single accept state, we get an interesting model. So for the model of unbounded width permutation branching programs with one accept state, this is joint work with Jose and Vadan, we obtain an explicit PRG with seed length log n times log 1 over epsilon, and actually a nearly matching seed length lower bound. So what's happened here is we've eliminated this log squared to n term from the Nissan generator, and we've also eliminated the log n times log w term from the constructions for small width, but recall that we're only allowing one accept state right now. So for the polynomial width regime, we might initially think that this construction improves on Nissan, because clearly there's no dependence on width. So if we specialize width to be polynomial in n, this is great. We're still not losing anything. But unfortunately, if we then take our error epsilon to be epsilon divided by w to survive a union bound over the w possible accept states for a polynomial width permutation branching program, this log n times log w term reappears, and we're back to no improvement. So we've started to fill in this chart, or this box. So for unbounded width permutation programs in the high error regime, we have a PRG with seed length log n log 1 over epsilon. But in the low error regime, where we divide epsilon by n or divide epsilon by w, we don't yet have a construction that beats Nissan or INW. So subsequent to that, with Vadan, we constructed an explicit weighted PRG for permutation branching programs of unbounded width with a single accept state with seed length this thing, which is log n times root log n over epsilon. So rather than log n times log n over epsilon, we've added a square root, and we have this log 1 over epsilon term. And there are also log terms that I'm hiding here. And so what this seed length gets us is we break the log squared n barrier of Nissan in the polynomial width regime. And that's because here, if we divide epsilon by poly n, our seed length doesn't change. We don't get any log squared n terms appearing. And in fact, we achieve seed length log to the 3 halves n for error 1 over n. And every 1 over n PRG for this model has seed length log squared n. So we actually give an explicit weighted PRG that gets better seed length than any PRG, which I think is another reason why this weighted PRG idea might be interesting. At a high level, this result comes from using spectral graph theory tools of Cohen, Kellner, King, Peebles, Peng, Rao, Sidford, and Ahmadinejad, Kellner, Murtaugh, Peebles, Sidford, and Vadan for a more sophisticated analysis of the prior error reduction procedure. We make 3 primary changes. First, rather than using Nissan as our base PRG, we use the PRG for unbounded width discussed earlier. Second, and this is the most involved part of our construction, we analyze the norm of this error matrix with respect to a matrix norm defined by some positive definite matrix F. And third, we derandomize these products of base PRGs using the previous result that it holds for high degree branching programs as well, which we won't discuss. So in order to analyze Richardson iteration for this, rather than working with the Laplacian of the branching program directly, we analyze the cycle lift. So we take the random walk matrix W of the branching program, which you can think of as all of the transitions from layer I to layer I plus 1, and we tensor this with a cycle of length n. And note that we, in order to maintain things like regularity, in order to make sure that the uniform distribution is stationary and things like that, and we need this for a couple of other technical reasons, we add edges from layer n to layer 0. And in addition, we multiply by some constant, which is slightly less than 1, so 1 minus 1 over n, and we do this so that the condition number of the cycle-lifted Laplacian only depends on the length n and not on the width w. And this is because if we had any dependence on the width w, w can be up to 2 to the n, so this would be very bad. The key technical lemma, which really builds off of these two prior works, analyzing Shor complements of directed Laplacians, says that given some error parameter delta and a permutation branching program with cycle lift Laplacian L psych, there's some positive definite matrix F and a weak estimate L psych inverse tilde constructed with the HPV PRG with error delta, such that now if we look at the norm of this error matrix with respect to this F norm, we see that it's bounded by delta times order log squared n. So previously we had something like delta times n by taking a union bound over the columns, and now we have delta times log squared n, which is much better. And in fact, this means that we can perform error reduction with base error delta 1 over polylog n. And just two notes, if you're interested, if this doesn't make sense, that's fine. F is defined in terms of the Shor complements of the cycle lift and has condition number poly n via the way we chose our weight. And the second thing that is important here is that we use the prior PRG in a white box manner, in that it's not the case that a generic PRG for branching programs with one accept vertex would immediately suffice in this construction. We do need to use other properties of that PRG. And so now we can put this construction together in exactly the same way as the prior result. We take epsilon to be epsilon over n to survive conversion from F norm to the conventional notion of max norm, which is what we want to get in the end. The initial PRG has seed length log n times log 1 over delta for this delta error parameter that we're going to choose later. And given our choice of delta, we set k in terms of that so that we do enough iterations. And then we get our final seed length, which is the seed length to select a term, plus the seed length to generate correlated seeds for an inner product. And this is k times log n plus our base seed length plus this term, which is coming from derandomizing the inner products again. And given the seed length, you can just do some parameter balancing so that the two components of the seed length are approximately equal. And you get the ultimate result of log n, or you get our final result of log n times square root log n over epsilon plus log 1 over epsilon. And again, I'm hiding some log factors. And so we can then, now that we have this low error construction for the unbounded width single accept vertex case, we can apply it to the bounded width case. Just by dividing by w, we obtain an explicit weighted PRG for permutation branching programs of width w that has seed length log n, square root log nw over epsilon, plus log w over epsilon. So what we've managed to do here is improve on the bounded width model by reducing error in the bounded accept state model. Because we went from log n times log nw over epsilon, now we've managed to add the square root. And we did this by first reducing error for a single accept state, and then using this mild degradation as we increase the number of accept states. So we might then ask, can this approach work for other models? We seem to need two things. We need some high error object to reduce the error of, and we need some error reduction procedure, which takes this high error object and produces a low error one. And so we've started to fill in this chart where we've added a weighted PRG, which obtains less than log squared n seed length for low error. And now we can move over, I guess motivated by how this chart is set up, we can move over to the right side and consider unbounded with regular programs. And we probably want to consider the high error regime first. So for unbounded with regular branching programs with one accept state, the prior result with Jose and Vadan gave a non-explicit hitting set generator with optimal seed length log n over epsilon. So this is not an explicit construction. It uses the probabilistic method, but it gets this optimal seed length. And in the recent joint work, we construct an explicit hitting set generator with seed length log n times log 1 over epsilon. And we also give a result that I won't talk about today, which is an error reduction-based hitting set generator for small width regular programs, which extends methods of Jose and Zuckerman. So it's probably time that I define what a hitting set generator is, and a hitting set generator can be thought of as a one-sided analog of a PRG. So it's some function, h, that takes s bits of seed to n bits of output, where for, again, some class of functions that we care about, for every function in that class with expectation at least epsilon, there's some x so that f evaluates to 1 on h of x. So h hits the set of strings on which f is 1, for any f that has sufficiently high expectation, which motivates the name. So what we do is we construct an explicit epsilon hitting set generator for regular branching programs of unbounded width with this seed length. So this matches the seed length of HPV for the permutation case in the regular case. So we've again managed to get rid of this log squared n and this log n times log w term at the cost of only allowing a single accept state. And in this case, rather than getting a pseudorandom generator, a PRG, we get a hitting set generator. So at a very high level, the proof overview of this result, it proceeds by showing that for every regular branching program with one accept state, we can approximate this regular branching program from below by some program B sub L. And what do I mean approximate from below? I mean that B sub L evaluates to 1 only on stuff that B evaluates to 1 on. And B sub L has 3 useful properties. The first is that it has width order 1 over epsilon. So epsilon is a parameter that we get to choose here. Not only does it have width order 1 over epsilon, it loses at most epsilon probability of accepting versus our original program B. So if B has probability of accepting 1/10, this has probability of accepting at least 1/10 minus epsilon. And finally, this program is almost regular. So B sub L is not a regular branching program, but it's almost a regular branching program in a suitable technical sense. And because of this, we show that it can be fooled by the existing PRG for small width regular branching programs of Braverman, Rao-Raz, and Yehudayev. And with this construction, we managed to fill in the third element of this table, where we obtain matching seed length, but with a weaker guarantee on the pseudorandom object. And I have slides which discuss this construction in more depth. If we have time and people are interested, I'm happy to go over them. But for the final official part of the talk, or the not slides part of the talk, depending on how you want to view it, we can ask, why is the fourth square interesting? So we filled in squares 1 through 3 here, and we have this empty square over here for constructions for unbounded with regular branching programs for low error. So why would we want to fill in this fourth square? By a result of Reingold, Trevisan, and Vadan, and that we extend in our recent paper, we show that if we have some explicit 1 over n to some constant, like I think 20 probably works, hitting set generator for regular branching programs with one accept state, then H is an explicit 1/7 hitting set generator for log space randomized algorithms. So what this means is a low error hitting set for a regular branching program with one accept state, this seemingly limited model that we've talked about, would break the 30-year barrier of Nissan for constructing hitting set generators for general log space computation. And so this is, I think, motivates filling in the fourth square. It also shows that filling in the fourth square is certainly a challenge. Like there's no direct port of the permutation methods, but I do think it's a very interesting motivating question. And finally, beyond that question, I think there are lots of interesting open problems related to this model. So the perhaps the most natural one would be PRGs or weighted PRGs for unbounded width regular branching programs versus unbounded width permutation branching programs where we have those results. And in fact, any two-sided de-randomization would be interesting. There's currently no two-sided de-randomization, and the lower bounds are, we have no lower bounds which are stronger than in the permutation case. And in fact, not only would any two-sided de-randomization be interesting, it wouldn't even need to be an explicit one. So there's no non-explicit PRG or weighted PRG for this model. And just in the permutation case, we do have recent work of myself and Vadan giving an optimal non-explicit deterministic sampler. So a deterministic sampler just makes queries to a function and then outputs the estimate. And even a construction of that for unbounded with regular branching programs is not currently known. The second would be improved weighted PRGs for permutation branching programs. And the third would be more and improved error reduction in other regimes. So our recent work gives a low error hitting set generator for small width regular branching programs. And I wonder if there could be a weighted PRG with matching seed length to that. And finally, perhaps the most broad question, but still one that has lots of concrete applications, is error reduction based on other algorithmic primitives. So error reduction based on this idea of viewing preconditioned Richardson iteration as a tool for constructing pseudorandom objects was able to give lots of interesting results, but it does seem to have some limitations. And in particular, the thing that we run into is that this selecting k pivots step in order to generate an output of these weighted PRGs seems to force parameter balancing, because you get a seed length of k times log n plus the rest of your seed. And so other algorithmic primitives here might not induce this extra seed length and enable us to do error reduction with better parameters. So thank you very much, and I'm happy to take questions.
So thanks a lot. As you might see in the chat, Rasmus left, so I'll take over because he has to run. Thanks a lot for the talk. Maybe I'll start out with a question. So you talked about this positive semi-definite matrix F that you use to get Richardson to converge.
Yes.
Like, how much do you think this is based on the structure of this particular Laplacian, or like, do you think this could generalize to different settings?
Yeah, great question. So the way we define F, I don't have slides for it, so I'll just stop sharing for answering this question, but I can go back, is we define it in terms of the short complements of the specific branching program that we want to analyze. So this positive definite matrix F actually depends on the branching program that we're analyzing the weighted PRG for.
Yes.
So and this is coming from this paper solving directed Laplacians via sparse LU factorizations, and some additional work via Ahmadinejad et al. But certainly, for instance, trying to apply this in the regular case runs into hard barriers. We need to use that the PRG that we have for the permutation case gives us a quite strong notion of approximation. So a notion of approximation for directed graphs. And once we have this, we can construct this F norm, which plays very nice, and we lose very little error but generalizing that to broader cases, I think, is a super interesting problem, but I don't have any idea how to do it right now.
Okay. Thanks.
Yeah, thank you for the question. If there are any others, I'm happy to.
If there's nobody else asking questions, I'll happily ask another one. Like, how useful do you think, like if you would apply these results to trying to sample random walks on graphs, like how easy is it to apply it to, like, say, a graph that's maybe Eulerian but not regular, or is it very hard?
So,
what do you think on that?
Yeah, what I should say is that this Ahmadinejad et al. Result, which gives algorithms for estimating random walk probabilities on graphs in small space, that works for Eulerian graphs, not just regular.
Mm-hmm.
So that does naturally port over. There's no real notion of an Eulerian branching program, or at least I haven't seen one. So we didn't sort of analyze it in the pseudorandomness context. But going from, I think one interesting question that I didn't put on the open problem slide is, for instance, can we use weighted PRGs for streaming algorithms? Because lots of streaming algorithms use results like the Nissan generator to reduce the randomness required. But a weighted PRG is a little different because it gives you this real number at the end rather than 0 or 1. And so could you use that to get lower randomness streaming algorithms is another question.
Yeah. Okay. Thanks.
Yep. Thank you.
So, are there any other questions of the audience? Feel free to ask. Yeah, if there's no further questions, we can also like switch to these tables and maybe talk a bit more informally if people are still interested. I would be certainly really interested to talk to you more.
Excellent.
If you would feel like staying for a few minutes.
So,
but yeah.
We seem to have timed this perfectly so that the live component ends in 10 seconds. So
perfectly synchronous.
Yes, great. So